Have you ever wondered why compasses point north, or how our planet is shielded from harmful space radiation? Invisible, silent, and constantly in motion, Earth's magnetic field surrounds the planet like a protective bubble. Without it, life as we know it might never have survived. This unseen force shapes navigation, influences technology, and protects our atmosphere from the powerful solar wind streaming from the sun. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today we explore what Earth's magnetic field is, how it forms deep inside the planet, why it sometimes shifts, and how it protects life on the surface. Earth's magnetic field originates far beneath our feet, in the outer core. The planet's core consists of two layers, a solid inner core and a liquid outer core composed mostly of iron and nickel. Temperatures there are comparable to the surface of the sun, yet immense pressure keeps the inner core solid. The outer core, however, remains molten and in constant motion. This motion is the key. As Earth rotates, convection currents form in the liquid iron of the outer core. Hot material rises, while cooler, denser material sinks. Because molten iron conducts electricity, its movement generates powerful electric currents. According to the laws of electromagnetism, electric currents produce magnetic fields. This self-sustaining process is known as the geodynamo. Unlike a permanent bar magnet, which has fixed poles, Earth's magnetic field is dynamic and constantly changing. The magnetic north and south poles wander over time due to these shifting flows in the outer core. This is why our maps need constant updates. The magnetic field extends far into space, forming a region called the magnetosphere. This region acts as a shield, deflecting most of the charged particles from the solar wind. Without this protective barrier, these high-energy particles would gradually strip away our atmosphere, as scientists believe happened on Mars. Earth's magnetic shield helps preserve our air and protects all living organisms from excessive radiation. When charged solar particles do manage to sneak through near the poles, they interact with our magnetic field and create spectacular auroras. In the north, we call them the aurora borealis, and in the south, the aurora australis. These glowing curtains of light are beautiful, visible reminders of the invisible magnetic field constantly interacting with space weather. The magnetic field also plays a crucial role in navigation. For centuries, sailors relied on compasses aligned with Earth's magnetic field to cross vast oceans. Even today, many navigation systems incorporate magnetic data alongside satellite positioning. And it's not just humans. Animals such as migratory birds, sea turtles, and even some bacteria are believed to sense Earth's magnetic field, using it as an internal compass during long journeys. However, Earth's magnetic field is not constant. Geological records show that its strength has varied significantly over millions of years. Even more dramatic are magnetic reversals. At irregular intervals, the magnetic poles switch places. Magnetic north becomes south, and vice versa. How do we know this? The evidence comes from patterns recorded in volcanic rocks on the ocean floor. When molten lava cools, iron-containing minerals align with the prevailing magnetic field at that time, locking in a snapshot of its direction. As tectonic plates spread at mid-ocean ridges, they create symmetrical magnetic stripes on either side of the ridge. These patterns provided critical evidence for plate tectonics and revealed a long history of magnetic reversals. Scientists don't fully understand exactly what triggers a reversal, but they are believed to arise from instabilities in the geodynamo. It's important to know that reversals happen over thousands of years, not instantly. During a reversal, the magnetic field weakens and becomes more complex before strengthening again in the opposite orientation. Naturally, some people worry about what would happen if a reversal occurred today. While increased radiation exposure in certain regions could affect satellites and power systems, life on Earth has survived many reversals in the past. There is no clear evidence that reversals cause mass extinctions. The planet has a way of weathering these cosmic storms. Modern technology, however, depends heavily on understanding the magnetic field. Satellites constantly measure its strength and monitor changes. Power grids must prepare for geomagnetic storms, which are disturbances in the magnetosphere triggered by intense solar activity. In extreme cases, strong solar storms can induce electric currents in power lines, potentially damaging infrastructure and causing blackouts. That's why space agencies study the interactions between the Sun and Earth's magnetosphere. Improving our forecasting of space weather is increasingly important as society becomes more reliant on satellites for communication, navigation, and climate monitoring. Earth's magnetic field also gives us a window into the planet's deep interior. By modeling magnetic variations on the surface, scientists gain insight into the fluid motion within the outer core. Seismic studies combined with magnetic data help us build a more complete picture of Earth's internal structure, a world we can never directly see. Comparing Earth with other planets highlights the importance of a strong magnetic field. Jupiter possesses a powerful magnetic field, even stronger than ours, generated by metallic hydrogen deep inside. Mercury has a weak but detectable magnetic field. Mars, however, lacks a global magnetic field today. Its early dynamo appears to have shut down billions of years ago, leaving only remnant magnetized regions in its crust. The absence of a strong magnetic shield on Mars may have been the key factor in its atmospheric loss, transforming it from a potentially wetter, warmer world into the cold, arid desert we observe today. This comparison suggests that sustaining a magnetic dynamo may be crucial for long-term planetary habitability. So what does it take to generate a magnetic field? It seems to require three essential conditions: a conductive fluid, sufficient internal heat to drive convection, and planetary rotation. Earth meets all three conditions perfectly. The combination of radioactive decay, residual heat from its formation, and the gradual growth of the inner core continues to power the convection in the outer core. As the inner core slowly solidifies, it releases latent heat and lighter elements into the outer core, further driving the churning motion. This ongoing energy supply has helped maintain our geodynamo over billions of years. Despite its overall strength, Earth's magnetic field is not perfectly symmetrical. It tilts slightly relative to the planet's rotational axis. It also contains irregular patches where the field is weaker. One such region, known as the South Atlantic anomaly, shows a significantly reduced magnetic intensity, allowing more radiation to reach low Earth orbit satellites. Scientists closely monitor such regions because they can affect spacecraft electronics and astronaut safety. Continuous observation helps improve models of how the magnetic field evolves over time. The magnetic field also influences the radiation belts, known as the Van Allen belts. These donut-shaped zones trap high-energy charged particles around Earth. While they protect the surface from this radiation, they also pose challenges for satellites that must pass through them. On geological timescales, studying magnetic minerals in rocks allows scientists to reconstruct past continental positions. This field, called paleomagnetism, was instrumental in confirming the theory of continental drift and mapping the history of plate movements over hundreds of millions of years. Earth's magnetic field therefore connects deep interior physics with surface geology, atmospheric protection, biological navigation, and modern technology. It is a unifying phenomenon that links multiple scientific disciplines in a truly remarkable way. As research advances, scientists continue to refine geodynamo simulations using supercomputers. Modeling the turbulent, chaotic flows of molten iron under extreme pressures remains incredibly challenging. However, improved simulations are bringing us closer to understanding how a stable, large-scale magnetic field can emerge from such chaotic motion. Future space missions will study the magnetic fields of other planets and moons in even greater detail. By comparing different planetary dynamos, we enhance our understanding of Earth's own magnetic behavior and its long-term stability. Ultimately, Earth's magnetic field is a profound reminder that our planet is not a static object. Deep within, molten metal circulates in slow but powerful currents, generating an invisible shield that stretches thousands of kilometers into space. This shield protects our atmosphere, influences climate stability, and makes life on the surface safer from cosmic radiation. Recognizing the importance of this hidden system deepens our appreciation for the delicate balance that sustains life. The magnetic field is not directly visible, yet its effects surround us every day. From the compass in your phone to the auroras shimmering in the polar skies. Its presence shapes both our science and our human experience. Understanding Earth's magnetic field also highlights how interconnected planetary systems are. Interior heat drives convection. Convection drives magnetism. Magnetism protects the atmosphere. The atmosphere supports life. Each layer of our planet interacts with the others in complex and beautiful ways. As scientists continue exploring Earth and other worlds, the study of planetary magnetic fields remains central to understanding habitability, planetary evolution, and the long-term future of our own world. This is Mattermosaic, piecing together the universe, one discovery at a time. If this exploration of Earth's magnetic fields sparked your curiosity, share it with someone fascinated by the hidden forces that shape our world. Tell us what scientific mystery you want us to explore next in the comments, and subscribe for more weekly journeys through the fabric of reality. Thanks for watching.